Okay, so today we need to talk about linear transformations. This is going to feel a little funny because we've been talking about linear transformations a lot through this semester. So I'm going to start with a little definition here. So our definition is going to be uh, a map T mapping, let's say, V to W. So that's going to be between, let me just write this here. So we'll just say V and W are vector spaces. Is called a linear transformation. Sometimes said operator. I'm really guilty of using the word operator and transformation interchangeably. Some authors take issue with that. I personally don't find that distinction to be super duper helpful, but I'll tell you what it is here in a minute. So a map T from between two vector spaces is called linear transformation if two things hold. So if T of u1 plus u2 is T of u1 plus T of u2. This should feel real familiar. This rule's been true for matrices, right? We've used this rule a lot. You've probably heard me ask you a question to which the answer was because A is a linear transformation or because A is a linear operator, right? A matrix is a linear operator. This is really helpful. Okay, and T of CU1 is C times T of U1. For U1 and U2 in V and C a scalar. Okay, so that's what a linear transformation is. That's this kind of definition that I'm making. I'm going to add this little caveat here. Some authors reserve operator for the case V equals W. In other words, some authors would say that a properly rectangular matrix is a linear transformation, but not a linear operator. And a linear operator is required to be like a square matrix, essentially. Um, I don't find this distinction to be super useful, so I use these. I use the words transformation and operator interchangeably. Strang doesn't care. This is kind of up to you or the author of your textbook. But I just want to throw it out there that you may encounter a difference. You may encounter somebody who believes there's a strong difference between these two, and that's like kind of fine. It's up to them. Um, so I'm going to have some examples. Like we know A is an n by m matrix maps Rm to Rn. So a matrix A is a linear transformation from Rm to Rn. Totally fine. Oh, I can't do the alphabet. Usually we go MN when we do the alphabet, but whatever. Same deal. Another example would be something like the derivative operator, which maps like the space of nth degree polynomials into like the space of nth degree polynomials. This is also like kind of convenient. I want you to notice here, like just kind of a quick note. A matrix is a linear operator or a linear transformation. It's not immensely clear here, so we don't yet have so we don't yet know that a linear transformation is a matrix. You've got to be a little bit careful with this today. We'll later have some like kind of knowledge about this, but for right now, I want you to know that a matrix is a linear transformation. A linear transformation is not necessarily a matrix today. There will be some criteria under which that's true, but not today. So, one other kind of important note This is an interesting one. A linear transformation is automatically a function, which is cool. Oops, that's not the best typesetting. So in order for something to be a function, I just need to know that it takes the same input to the same output every time. So I'm going to prove this by just quickly supposing it's not. So let's suppose t takes u to v and t takes u also to w. Right, so that's just us supposing that it takes the same element into different places. Well, then I would know that I'm going to look at v minus w. So let's just consider v minus w. Well, v minus w is t of u minus t of u. But t of u minus t of u is t of u minus u, which is t of the zero vector. And t of the zero vector has to be the zero vector. You might spend a second and think about why that's got to be true, but that does have to be true. So I'm gonna kind of leave that as a little thought here. This is actually in the homework in Strang. So why do we know that t of 0 has to equal 0? Cool. All right, so once I know that this is the 0 vector, then I know that v and w are the same vector. So v and w couldn't have been different vectors. Great. Awesome. That implies v equals w. Check. Okay. Couple of more little facts, little tidbits here. These are just kind of assorted facts. My assorted facts are, if we know t of xi for a basis, let's just say all xi in a basis, this means that we know t. So we know t of a vector v for any v. That's kind of a cool fact. We just need to sort out how our transformation acts on basis vectors, and then we can immediately know how it acts on everything. That's really because we can write any vector v out in the basis, and then we can use the linear operatorness to kind of pull that thing apart. We can factor all the constants out front, and then we can do t to each of the basis vectors, which we already know from the kind of first assumption, and then we could multiply by the scalars and smash the whole thing back together again. Great. That's kind of cool. Let's see. Other things. Pseudo-inverses are kind of interesting. So you might consider what's a pseudo-inverse? Well, it's an inverse, but it only works on one side, maybe, or it's not quite a complete inverse. I'm going to kind of leave this thought to you guys. There's a couple questions in the section about what the pseudo inverse for the derivative is. This is really interesting. You just spend a minute thinking about that. If you do none of the other homework problems, that's a good one. Another kind of, I guess I called these facts. Let me call these facts or points of interest, maybe. Maybe instead of R, I mean, is there always a matrix? I kind of teased that. So you could kind of think about that. That would be an interesting question. So an example of something that you could lay your hands on that would be kind of cool is maybe find a matrix for the derivative mapping second degree polynomials to second degree polynomial space. That should be a relatively doable thing. Find a matrix for the pseudo inverse would be a cool idea. Like, what is the pseudo inverse would be a cool idea. I just kind of want to leave you with a couple of questions today. The linear operator stuff, just be sure that you're not assuming that they're all matrices right now. There's like kind of interesting work to be done in the homework using just these two properties. So have fun, enjoy. This is like a nice kind of abstract thing to like leave the course on.